Okay. Yeah, it's all set. Okay, today's class will be actually a bit light class because I will mainly talk about some, I mean, I will talk about some ideas and applications of second quantization, which are too heavy to talk in detail. So that's why I'll talk in very less amount about it. And just to give you a motivation that why we are doing all this. And then I hope that will take about 20-25 minutes. Then I'll move on to a new chapter, that is perturbation theory. And again, I will give an elementary introduction of perturbation theory. And then from next class, we will go into the full rigor of perturbation theory. Perturbation theory is a easy chapter because it's nothing but a technique to solve problems approximately, but it requires you to sit down and do calculations, lot of long calculations. Otherwise, you will not follow what is going on. But it's easy also at the same time. It's just calculation, just manipulation. Okay, but it also gives some insights, but those are, I mean, not that hard. Okay, so this is the plan, and yeah, so let's start with and the good thing is that for the perturbation theory, I have very well written notes and very well prepared pre-recorded lectures, so that I will also give you. And this, interestingly, so I bought my tablet today because right after mid-sem pandemic happened in 2020, right, if you remember, and then I had to switch teaching online, and I thought that I will teach in slides. Okay, so I made slide one lecture. Okay, that was the last lecture ever where I made slides, and you will see why. I will give you a time-dependent perturbation theory note. That it has 100 pages of equations. Okay, so if I had to make that much slides, my whole time would have gone. So I have only one lecture in slides, which I will give you, but I will. That's why I brought the tablet. I could have printed it also, if I get to do some perturbation theory today. Okay, but other good part is that, so when again the pandemic started and many people were teaching using a board, and each lecture became like 700 MB or something, and then the students complained that we can't, our data is not that much. So then I had to make those lectures which are 1.5 MB each. And it's not hard, it's just that if you don't appear in the video, it will become small. And it is, and I have those videos very nicely prepared, and which does all these detailed calculations, discusses all that. So the good part is actually I don't even need to teach this section. I can chill and I can give you those things and discuss here. But anyway, my experience is people don't study unless there is a fire on their tail. So there has to be something happening here and pushing. Okay, if I give you lectures and expect you to study, that will not happen. Right? Okay, so let's finish off this chapter, which is second quantization. So I will recap a little bit, and okay, I will show you some outline of a more rigorous calculation, that a more rigorous approach, that how do you get this kind of a all these things which we have already talked about in a more intuitive way. And we learned about two set of rules. One is for fermion, another is for boson, and those rules were that dk for nk is nk minus 1. This is for boson, and bk dagger is okay. And similarly for fermion, we found what was that, k less than something. What was the notation I used? Okay, I should use a different notation. I less than k. If I writing things from the left side, but it doesn't matter what convention I use. Okay, it's not nk, by the way, it's 1k, because there is no concept of that. And if k dagger acting on 0k will give me minus 1 to the power. Okay, these were the set of rules. And more importantly, we found these rules will give you this anti-commutation, although we didn't cooked up it like that. We said, okay, first anti-commutation, which we need to satisfy this anti-symmetric property of the wave function, and exclusion principle. And we said the kind of operators, the way I can define my creation annihilation that gives that is this. So this will imply, I asked you to check that dk prime is delta kk prime, and all other things, that bk and dk are 0, and similarly for fermions it is So this behavior is actually very important. You will see that you have to, when you do field theory for fermion and boson, you will see for fermion you have to invent a new kind of numbers. They are called Grassmann numbers. They are quaternions. They are even simple arithmetic is different from regular arithmetic. Okay? So that's very interesting. That how for a certain kind of property you need to expand the regime of things in math, and then that allows you to give a proper description of it. You have to invent the calculus of those numbers. Everything is separate from there. Okay. So now we will say a little more rigorously, which I will not fully prove, but I'll give you some idea that how it comes naturally. That if I have a pair of operator, I call it A in my notebook. So let me call it A. That satisfy this property. That let's say I start from this and see naturally this thing will lead to that. And there is a number operator which is given by this. Okay. So let's see what can I say about such an operator. Okay. So it turns out that I can define a eigenvalue of this eigenvalue equation for this operator, which I call phi. And I can immediately see that because phi is 1, okay, so then I can call this thing. So I can define an object called phi n phi, which is the some expectation value of this operator, which is a dagger phi a phi, and this is nothing but a phi square, right? This square is conjugate, right? So it is nothing but this. So then this must be greater than 0, okay? Since it's a squared object. Okay? It's a number, it's a squared number. So that implies that, so if I call this quantity, let's say call this phi, a phi, so that tells you, sorry, phi is a phi mod square. That implies phi is greater or equal to 0, and there are, that means this eigenvalue is always a positive definite, right? And positive semi-definite actually, because 0 is included. Okay. So the lowest number is 0, phi is 0, and that implies a phi is 0. Okay. This is the bottom of that rung, bottom of the possibilities. Okay. The lowest is 0. Okay. So now what more I can say about this? So let us say I want to act this n on a chi. Okay. And what is chi? Chi is basically a phi. So n acting on a phi. What more can I say about this? So notice that what did I find? I found that there exist, I started with only these two things, right? I defined an expectation value. I said that this thing must be greater or equal to 0 because this is a square. And the lowest value it can take is 0, and the lowest value must be a condition where a acting on phi is 0. Right? This is what I found. So now I don't know yet, although I have shown you all those things already intuitively, I don't know yet what is this a phi, okay? Because we have not defined anything. So let's try to figure out what is this a phi. So to do that, I want to ask what happens if n acts on a phi. Okay. So what more can I say? So I can write this as n a. So this is an operator also, n a phi, because n a phi is n m minus a n, right? So that means I have to add a n phi, right? This is this, right? But what is na? So na is a dagger a, right? Now I can use this ABC, this commutator rule. So this is a dagger a, that is 0, and next is a dagger a, which is minus a. This is 0 and this is minus, because a dagger is 1, so a dagger a is minus 1. So this is minus a. So what did I find? Minus a phi plus a n phi. Okay. There is no mystery in that because I have just used the commutator. So now that means what? So yeah. What is what? Chi. This is chi. Chi is a phi. Okay. Yeah, it's just defined. You can remove that line also. It doesn't affect anything. I'm just seeing this action. Okay. What happened to you? Oh, you are writing on tablet. Okay, I thought you turned Stephen Hawking or something. Okay. Okay. Why is it using a laptop? Yeah. So only once I wanted to be high tech. That was when I tried to make slides, and I said it's not worth it. Okay. It requires some practice though in writing in this tablet, because when the first lockdown happened, institute still didn't have this policy to give to funding for tablet Mac, all these, what is this called, Apple tablets. So I bought one such thing, and it took a lot of learning to how do I write by not staring at the surface where I'm writing. Yeah, you have to. It takes a lot of practice. So initially, I was not taking writing in the classes in real time. I had pre-written, and people complained, no, it's too fast. So then I had to practice that, and then by then the tablets came, because your line will not be straight. It will like go like this, and all those things will happen. Okay. Okay. What I want to try to prove. So na phi is, yeah. So I know this equation. So let's use this. So n a phi. Now a n phi is basically phi phi, and this is minus 1. So this is phi minus 1 a phi. Right? I just use this. So this n phi is phi. So this is basically phi a phi and minus 1 a phi. So this is phi minus 1 a phi. So now I have naturally defined that this naturally leads to the fact that a phi is a type of annihilation operator. Because what happens when you act? If a state phi, its number operator gives you phi for that, a state a phi for that the number operator will give you phi minus 1. Right? So you can construct the whole machinery by doing this. Okay? So the reason I wanted to, I didn't do it, it might be satisfactory to do it like that, because many times the textbooks are written like that, but the reason I did it like that, because often things are not discovered like that in a sane, mathematically beautiful way. They are discovered in physics with intuition. You cook up what you need, then you find if there is something like that in mathematics. And often, many cases, it turns out it happens. Like Heisenberg wrote down matrix equation without knowing about matrix or linear algebra, anything. Okay. Okay. So now, what else can I talk about? Okay. Yeah. So naturally, it says that then I can keep going down like that, and there must be a point where I cannot go below, because these things cannot go below 0. Right? So there must be a point which gives you this a phi equal to 0. So this is a very intuitive idea, and it comes very naturally from all that. Okay, now I can climb up in this ladder, and I get all these harmonic oscillator things, which I will not show again. And basically the idea is, if I have a set of operator like this, and it has there is a number operator, then you naturally lead to this kind of and go down by A. And now the question is, how do you interpret it? Now interpretation is very deep, that I will tell a little more about it, because it paves the way naturally to field theory. But you have learned that two way of interpreting this in already. One in the context of harmonic oscillator, also in angular momentum algebra, that this is a way to go from one state to another. And now you have learned this is a way to create particles, where you are adding particle into the system. The same formalism works in both ways, right? So this is one, and why it works in both ways, that means there is some connection between these two, right? So that is interesting question, and that is what will take us towards field theory. But let's now talk about what happens for fermions, what this machinery gives us for fermions. So let us say I have fermions, and fermions have this f dagger equal to 1. Okay. So that means I again can show that there must be a n phi equal to phi pi, and by the same token, nothing changes here because of commutation and all. By the same token, there must be a f phi mod square, which is greater equal to 0. There is nothing changing here yet, but we'll see there is some interesting consequence of that. Now notice this is slightly different here, because this is basically phi f dagger f phi, that is greater equal to 0. Okay. Now that means we know that this thing implies that f dagger plus f dagger f is equal to 1. Okay. So this thing is 1 minus f dagger, right? So that means, and what is 1 minus f dagger? So I have defined this phi tilde. Okay, let me define something more. Let me define this thing as phi tilde. So now phi f dagger f phi greater equal to 0. This implies 1 minus f dagger phi greater equal to 0. And this thing is also 1 minus phi tilde. Okay. Why it is also 1 minus phi tilde? Because instead of this, I am saying just f dagger phi. Right? So now this implies, if 1 minus phi is that means phi must be less than 1. Okay? Phi tilde. Oh, this thing, if this is phi tilde, so this thing, when I expand this is also f dagger, right? Instead of calling this f, I can call this, so 1 f dagger is basically f dagger phi mod square. F dagger phi f phi. Okay. Okay. I think I started with the wrong equation. Yeah, I think I should have started with this. I should use the phi directly. So my phi is f phi mod square. So I should start with this. So f dagger phi mod square. Okay. So this is basically phi f dagger, and this is basically 1 minus F dagger F phi. So that is 1 minus phi tilde. Okay. Okay. Now I have to prove that this thing is also greater than 0. How do I prove that? Okay. So this I can. Let me see if I miss something from. Okay. Let's not skip steps. So fine. F dagger phi. Okay. So I have to show that this thing is greater than 0. How will I show that? Ah, it has to be greater than 0. Okay, it's so trivial because this is also a square, right? This is also a square. So I should start with this. Okay. So I land with this conclusion that 1 minus phi is greater or equal to 0. So that means phi must be less equal to 1, right? Phi must be less equal to 1. But the other way also shows that this must be greater or equal to 0, right? So that means the phi must be, right? Yeah. So no, here also it has to be 0, right? Greater than 0 has to be there. Now it has to be less than 1 also, right? So that leaves you with the possibility that it must be stuck between these. Now I have not yet proven it is discrete, right? I have proven that this must be 0 to 1. But I can also prove it discrete, just like before, because if I can show that there is an operator which does this, okay, that means it must go by 1 steps, right? So that means there are only 2 steps, 0 and 1. There is no other steps, right? And that I can also show just like before, right? Okay, so this is the only step I jump, and I ask you to fill this. Okay. Now this step requires a little bit of work. But it is positive definite. Yeah, this is what it shows, right? This is greater than 0. This is phi tilde is greater than 0. Yes. Both phi and phi tilde has to be greater than 0 because this quantity can be written as square always, right? But in this case, that phi tilde can be also written as 1 minus phi tilde, right? So that is why you are getting this thing. Okay, everybody is clear about this? Okay, now you show this. Now this is slightly different from before because earlier you remember to prove this we have used this, right? We have used this thing, but now you have to be careful about what is this because this is not a commutator. This is an anti-commutator. So that part is little bit of work. So using that you can show that this will also do that, and you can also show this must be always true. Okay. So if you show that, then it naturally gives you the ladder operator, and it also tells you there are only 2 possibilities, that is 0 and 1. So if I look at the harmonic oscillator equivalent of fermion, there are only 2 states, and that's it. Okay. So this whole thing comes from one thing, one idea, that is they are commuting or anti-commuting. Nothing else is required. So this is the afterwards way of making this thing look more mathematically elegant. But we already know that how we landed on the necessity of an anti-commuting and commuting object from pure physical argument. Okay. Yeah, is it all clear? No doubts, right? Okay. Yeah, you don't look very convinced. You are convinced. Okay. Okay, what else? Now I can go a little bit talking about some more points. Now I will tell a little bit of some sketchy things to tell you that why do I care about all this, and you will learn it in proper details in advanced condensed matter and QFT. Okay, so let me say in various side, there are many things one can discuss for it. This I'll tell a little bit about some of them. Okay, one thing I just want to tell you, just mention you, and I will not show you, although this can be shown in explicit details, is that you can write even an interaction term. For example, an interaction that is taking you from a V that is like this. Right? There are two particles. They are tagged as 1 and 2, and a V is an interaction between those two particles. Right? So this thing you can write it equivalently in second quantization language as some Ni, like N1 and N2, like in this way. So which is basically V AI A1 dagger A1, A2 dagger A2. So this kind of forms. Okay. So let me not, I will not show you right now here how to do it, but you will find it in any textbooks. But let me just show you some general forms. So, for example, one of the most standard model in many particle physics is the model where you describe electrons in a solid, and the electrons can hop from one side to another side, which you write it as Ci plus 1 dagger Ci. So it means it is destroyed at I and created at I plus 1. Okay. Now this has to be Hermitian, because if this process is allowed, this process has to be also allowed with equal probability. Ci dagger Ci plus 1. This is the Hermitian partner of that term. Now there can be another term which is Coulomb potential, when two particles sit on top of each other, right? So then there is a Coulomb. But now you have to be careful. It cannot happen if they don't have spin, right? Because spin and opposite spin. Right? If they have same spin, they cannot do it. So now you put a spin index in I sigma, in I sigma bar. Bar means if this is up, that has to be down. Right? So this tells you a Coulomb term. So you can write it also as, yeah. Of course, there can be a term also when the particles are far apart, because Coulomb is a long range force. So then there can be a term which is in I sigma, in I plus 1 sigma, or any far apart, but far aparts are very weak, so I'm not writing them. So this is a very standard way of writing a model of a solid. Okay, this is called Hubbard model, and all the interesting thing you see in solid state physics are basically something to do with this model. One way or the other, things are here and they are changing and all. There are actually more kind of terms. I'm not writing spin orbit coupling and all that, which have couples these things for a particular spin component and another particular spin component and all that. Okay? And there are, as I said, that so far probably you are only learning this much. Okay? which tells you all these band metal, band insulator, semiconductor, and all those things, right? This is what you are learning now, all these electron hole, all those concepts. So this will give you this block theorem and band insulator. There is actually another term which I missed. There is on-site, there can be an on-site potential, which I write as mu I Ni. So this U, when the U comes into picture, the Coulomb cost is too strong for one electron to move into another side. Then it also gives you the realm of strongly correlated systems, right? Where there is not just kinetic term, but there is a potential term which is very strong. Okay? So then when U is very strong, you get Mott insulator. And the physics of Mott insulator is very interesting. Actually, insulators are more interesting than metals sometimes. You might think, okay, nothing is happening there, but there are more things happening because you can show that some interesting phenomena happens here called charge spin separation. That because of the Coulomb cost, the charge cannot move, but the spins can fluctuate. You can show by doing a second order perturbation theory, you can show that this leads to a spin motion. And the electron behaves as if like its charge and spin are two separate entities. So only coincidentally, each of these people won a Nobel Prize for finding their respective things, like their insulators. Another is Anderson insulator, who also won a Nobel Prize. Which happens because the mu I is random, disorder. If nothing is present, the U is 0, V is 0, everything is 0, only mu I is there and T is there. The mu I is random, that gives you Anderson type of insulator. And it's very interesting. It tells you even a little bit of disorder will make everything insulator in 1D, which is not hard to see because let us say I have a 1D chain and I have some disorder, little disorder. Then the electron can no way go without seeing it. Right? There is no path. Now 2D, of course, there is a path. There must be a path, right, to go around that. But it turns out even in 2D, even it completely localizes it. It has to see that path. Very non-intuitive result. This was shown by gang of 4, which is Anderson, Abraham, I am forgetting one more person, T.V. Ramakrishnan. So this famous paper. And in 3D, it turns out a little bit of disorder will not localize, which means electron can go around without seeing the disorder. But if you increase that lot of disorder, then of course it will at some point in time get affected and localize. So there are a lot of interesting physics into this. Now each of these terms you had, it opens a new dimension of phenomena, right? When you have Coulomb potential, when you have, so now you can ask what happens if this localization physics, when I have U or B, okay? And if something localizes, how do I know it is because of this or this? Right? Those are very, what can I do? Let's say I'm an experimentalist and I have, all I can measure is current and voltage. Then what should I do to know what is happening? Right? These are very interesting research questions. If U and B are finite, it gives something called MBL, which yet have not won a Nobel Prize, but it should if somebody shows that it is stable. So there is a stability question of this kind of MBL. They are theoretically predicted, but their stability is an issue. That's why experiments are, it's not easy to see in solid state system, but it can be seen in cold atom systems where everything is controlled and engineered. Okay. So this is some aspect. There are a lot of other aspects. You must have seen another, you have learned how to calculate bands, right? For example, if I give you a simple tight banding model, you may not have seen in second quantization language, but if I give you in first quantization, in our the way we learned before, I plus 1, I, right? If I give you this, how do you calculate the band of this? If it is 1D chain, then you know that the band is cos kx, right? You learned this, right? 1D band structure. You're studying from Kittel, right? This all worked out in Kittel in one way or the other. And that I don't remember, but you get these band structures. Brillouin zones, all those things you learn, right? So this is all coming from there, right? It is just all those things is nothing but quantum mechanics on a lattice. There is nothing more into it. Right? So you will get this kind of a band structure. Now there are very exotic kind of band structure you can get. For example, if your lattice is a honeycomb, okay, then you get something called this kind of a band structure. This is like a Dirac cone. This is called a Dirac cone. You can show their behavior is like relativistic systems, a Lorentz invariant system, and you need a Dirac equation to describe them, not Schrodinger equation. Now it's all a magic of various things conspiring together to give you various exotic band structures. And there is another class of problem where you see notice that what is this? This is basically a kinetic term, right? And you know the band structure basically gives you is effectively like a kinetic term. So you can see some systems, these are very interesting these days, gives you a flat band, which means Ek is not a function of k. It's something like this, flat band. So if it is a flat band, then for such systems, the U will dominate the physics. And if U dominates the physics, a completely physics of correlated electrons. So one example is fractional quantum Hall effect, and there are many other examples that people are doing these days. So this is one set of a whole class of things that you can study using this second quantization language. And remember I told you earlier that this has to be Hermitian. Right? And we know that, because Hermitian means real eigenvalue and all that. But this is a completely, it's not that only Hermitian matrices have real eigenvalues, right? Also other matrices can have. So there was a very interesting problem studied by Hatano and Nelson, who showed that if I think of a gauge field, right? So this is, we know if I have a gauge field, the kinetic term instead of p square by 2m becomes p plus Ea by m square, right? So what is said? If my A is an imaginary number, Ig, so then what happens here? So first of all, if A is real, then you can show this appears here as some I phi, e to the power minus I phi and e to the power plus I phi, which phi is A dl, A dot dl. Now, if it is imaginary, then you get a phase factor which is just G and minus G. That breaks the hermiticity. Right? And you can think this kind of imaginary magnetic fields appearing in vortices of superconductors. So you will learn maybe your solid state physics, I don't know if it has, maybe near the end you will learn a little bit about superconductors. I'm not sure. Do you have superconductor in your syllabus? Towards the end, right? So you will learn a little bit about it. So it can happen in certain kind of superconductors, and they wanted to describe that, so they came up with this non-Hermitian picture, and that is very extensively studied these days. You can ask your senior Yash; he is doing some problem based on that. So we found some that recently how people are calculating dynamics in this thing is not entirely correct and all that. So there are many interesting problems associated with that. And second quantization makes all these things really simple. Okay. Now we'll talk a little bit about oscillators, basically harmonic oscillators, and tell you that how it paves the way for field theory in a natural sense. Okay, so there is one more thing I would like to emphasize on, which is not often talked about. So field theory is basically description for many particles, actually infinitely many particles. And you picturize your vacuum, and you picturize this creation and annihilation operator, that something creates particle from vacuum. Right? Now, that is what we also have seen. If you think of an electron hole picture, there is also, I have a Fermi surface and I can create and excite an electron and create a hole and electron. So particle, antiparticle, like that. So this picture in condensed matter physics, it is naturally like that. It's many particle. You don't have to do anything, because you're beginning with a system which is infinitely many particle, and you are calling that infinitely many particle as vacuum. Vacuum or ground state, whatever you want to call it. In particle physics, we call it vacuum. Here, yeah, hole is a antiparticle, right? So antiparticle is also absence of an electron from its vacuum. Right? You will learn that. You have not learned about antiparticle yet. You will learn near the end of this course. So this picture appears naturally in particle. This picture appears naturally in condensed matter physics because you are dealing with many particles anyway. You don't need Lorentz invariance for that. But it's a separate question that how Lorentz invariance becomes emergent at low energy. That's a separate question. But what happens when you learn about Dirac equation? You will see that you will be forced to describe vacuum as infinitely many particles. Now this is strange, right? So it's supposed to be no particle. Now it became infinitely many particles, right? And you will see that. I will not jump steps. We will see when we go there. Okay? So that's what unifies these two subjects. Okay? That you have to have a framework which is ready to deal with this kind of many particles. Right? Even to describe one particle in relativistic theory, you need this notion of infinitely many particle vacuum. Right? So that is why it appears naturally. It leads naturally towards this kind of a framework, a second quantization type framework. Okay? Now I will tell a little bit about. So one more thing I want to mention, that particles and fields, they are two different objects, right? In classical mechanics, particles are well-defined lump of matter, energy and mass and everything, and fields are something that is spread over, like gravity field, electromagnetic field, or even simpler things like if I have a box of fluid with something in it, there is a pressure field and all that. Right? All kind of fields are there. So in classical mechanics, they are separate objects, very well defined. But in quantum mechanics, they are kind of same thing. You will see that you cannot isolate the notion of particle and field. Now let me give a very brief idea that why it might be the case. And the idea is very simple. It comes from very simple notions of harmonic oscillators and that kind of thing in classical mechanics. So let us say I have a bunch of harmonic oscillators. Right? And you have learned about normal coordinates and all that, right? How do you describe such a thing? So I can say this is n equal to 1, 2, 3 Pn square by 2m plus k xn plus 1 minus xn. And I can calculate the classical equation of motion, which is basically del H del Pn del Pn. No. And if I do this, I will just get that d2xn dt2 is basically k by m xn plus 1 minus xn minus 2xn xn minus 1. You can also calculate this without going through all this. It's basically Hooke's law, right? The Hooke's law tells you the force on this particle in this direction is xn minus 1 is proportional to displacement, right? It's just that, Hooke's law. So this tells you this is actually a wave equation. Why? Because this is already a second derivative, and this is also a second derivative in discretized form. Right? So this kind of thing has a natural solution of this form. Yes. Yeah. What? Nothing. Okay. Sorry? No, all that. Oh, you are saying why it is second derivative? Yeah. Oh, this is just what is a derivative? A derivative is so xi plus 1 minus xi by I plus 1 minus I, right? Where if instead of I call it delta, and I take limit delta going to 0, then it's a derivative, right? So similarly, you can define second derivative. Then you will get this. This is finite difference formula actually. I don't know if you have seen it anywhere. Okay, so then that implies it has a natural solution in the form of wave equation. Actually, instead of x, okay, I should write an, because x is displacement, n is the actual coordinate. So this will be the form of the solution for this. This is the answered solution, and that gives you this. Also, you have learned about phonons in solid state physics, right? This is basically that exercise. Okay. So then you get a omega, which is 2 capital K by M sine K by 2, small k by 2. Okay. But you can start. It is start. It's conjugate of that. Okay. So now you see that, okay, so now you can go a few more steps. Okay, before I go to few more steps, I will tell you that what can I do for the equivalent continuum problem. Okay. So let's say I have a continuum problem, which is this, a string which is, I want to describe a string which has some deformation. Okay. And the deformation is only in this plane. Let us say only in this plane. So this is u, and this is my xn, and this is x. Okay. So this slope is basically grad u or del u, okay? Del u del x. So you know that such a string will have, if you don't know already, I'll show you later in QFT course properly. This is dx 1 by 2 rho p square x plus k by 2 del u del x square. Okay. So this is also like an oscillator, and you can show that this will have the differential, the equation of motion for this will be d2x dt2 kappa by rho d2u dx2. Okay. And that will also admit a solution of this form, uk e to the power I kx minus omega t and so on. Okay. So this correspondence tells you one is a discrete problem, a particle problem, and its solution is also some collective excitation form, which is this. And without even also going through all these details, you can just see this is a differential equation, it has a solution. I can do a Fourier transform always, right? And write it as a bunch of oscillators. Right? So this now can lead to a description. So now you can shift to a coordinate, which is dk uk 2 rho L omega k, where L is the length. So this is a little bit of algebra, and that will transform your Hamiltonian into omega k dk star dk. This will transform your Hamiltonian into this. Okay. Now notice I have not done anything quantum yet. It's just variable transformation, writing one thing in terms of another and going to a Fourier space. Now I can get into, so, and we have already done this when we discussed harmonic oscillator in quantum 1, where when I told you why we need this kind of creation and annihilation even in classical mechanics. So now I can define a qk, which is 1 by root 2 omega k dk plus dk star, and a pk, which is minus I omega k by 2 dk minus dk star. I can define these two quantities, and this will give me h is equal to half pk square plus omega k square qk square. So in simple words, I started with two different problems. One is a continuum string equation, another is a discrete set of oscillator, coupled oscillator, all harmonic, all linear. So the most important point is all these are linear equations. That's why you landed on this kind of a linear differential equation. You can in principle have more complicated terms into it. Higher powers of phi, that will give you nonlinear. And we'll learn in QFT how to deal with that in perturbation theory, but that's everything is linear. So both of these problems can be mapped to some kind of discrete harmonic oscillators in some other space, okay? In some case space, basically collective excitation space. And once you have that, you can second quantize it. Okay? You can second quantize it, and now you can go towards quantum mechanics. Right? You can now everything is classical so far. I have just shown correspondence between a continuum and a discrete problem, and both of them can be described as a harmonic oscillator. And then I can quantize it and use the usual thing. I can do the qk, pk, IH bar, and then I define another set of AK operator, which is their creation and annihilation, and go to this all this harmonic oscillator in Fock space. Okay. So I can continue to talk a little bit more about it, but this is your hint. This is an outline that why you might need, why there is a possibility that everything that has a linear equation, no matter what it is, can be described as can be quantized like that. Okay? So we will see it in much more details in quantum field theory, but for now is just to get an idea that why all these problems are equivalent. And it becomes a little more tricky when your this object is E square plus B square, which is a gauge field, the electrodynamics, because then you have to operate with the gauge constants, okay, and that is the QED. Okay, so that's all. I'll start with perturbation theory in next class.